I have change.
Yeah, I was going to buy another one of those.
How much change do you need?
Out of 10.
I have 1, 2, 3, 4.
How much you sell?
I have a 10. That's all I have.
How much?
Well, if you got 5.
Okay. Okay, so this is the DC circuits class. This is our second class. And I'm going to go ahead and check homework really quick. And then we'll talk today about static electricity. Almost primarily today just about static electricity. And then next session we'll talk about current electricity.
Mr. Austin, I thought it was reading.
I didn't see no homework. It was just reading.
Oh, that's right. There's only reading.
Yes,
That's right.
reading.
That's right. Clarence is here. Corey Adams
That scared me.
here. Gary Nichols is here. Robert Lambert. Oh, we're back there. Okay. Yeah, just Dakota's here. Benjamin Bettinger. Benjamin. Benjamin. Is he not here? Frederick Garrison.
Yes, sir.
Frederick, okay, got it. All right, and then we have Christopher was here, right? There you are. Donald was here. Back there's Donald. And I've already checked your homework. And Jesse, I got your homework earlier, right? Oh, he actually did the reading. That was from the last one. Yeah, we just had the reading. I'll give you guys credit today because we didn't really have a homework assignment. I mean, we didn't have we had a reading assignment, but we didn't have a written assignment.
Right.
Written assignment. Okay. I do have an assignment on the board. Make sure everyone copies down the reading assignment. It's sections, not pages, not chapters, not anything else. It's just basic. It's paragraphs. I guess you could call them sections. Topics, really.
Right.
Each topic is numbered. And one good thing about this book is you should learn at least one thing from each number that's up there. At least one topic. Think of it as a test question. Each paragraph you read, you need to glean something out of it. And you need to remember it. Okay, for the test. Because it's a concept that you need to remember. 147 through 158, 184 through 197, 326 through 330. So this talks about batteries, the first section, electromagnetism, and then magnetic induction, electromagnetic induction. So, okay. So we'll watch a quick little video.
Book 1823. 17-year-old Benjamin Franklin arrived in the bustling city of Philadelphia in 1723. He was a destitute runaway from his older brother's printing shop in Boston. Within a decade, through his potent combination of skill, hard work, and business sense, Franklin emerged as the leading printer in Philadelphia. At the age of 42, he retired, a wealthy man in the city of brotherly love. With his printing empire established throughout the colonies, Franklin was now free, he said, to devote his life to science and the improvement of mankind.
Anyone who was like a gentleman, which meant you didn't have to work for a living, was sort of expected almost to be dabbling in science. And I think Franklin kind of grew up in that era and wouldn't have hesitated for a moment to feel that he himself could also be involved.
Franklin threw himself into the most exciting area of 18th century science, the study of electrical fire.
Before Franklin came along, electricity was sort of parlor tricks, people doing static electricity and making sparks, but Franklin tried to make it useful.
Franklin's most significant theoretical breakthrough was to determine that everything in the world contained electricity. Franklin also challenged the prevailing theory that there were two different types of electricity.
The theory was that they would come together and one would cancel out the other. So Franklin comes along and he says, well, I don't think it's like that. I think there's just one fluid, but it can be positively or negatively charged, and it can flow off an object onto another object.
Franklin believed he could be the first to prove that the electric sparks in his laboratory and the lightning that came from clouds were one and the same. In his book on electricity, Franklin described what became known as the sentry box experiment. A Frenchman, Thomas François Dalibard, who had translated Franklin's book, decided to try it. A sharp metallic rod extended from a wooden shed that protected the observer from rain. If the rod, which was insulated from ground, drew off electricity from a storm cloud, the observer could draw off sparks with an insulated ground wire. And the sparks flew. At about the same time, he performed his own, potentially very dangerous test back in Philadelphia. In place of a tall lightning rod, he thought that a small metal point on top of a kite would draw electrical fire from the storm clouds and conduct it to a key dangling from the end of the string. When the key at the end of Franklin's kite string drew off sparks, it confirmed the results of the sentry box experiment. Thunderclouds contain electricity, and lightning is an electric discharge. Proving the electrical properties of clouds was a breathtaking discovery. But practical-minded Benjamin Franklin wasn't satisfied.
He said, we've studied the theory, but we don't have any practical use for it yet.
The practical use became the lightning rod.
The lightning rod stood on the rooftop. It was bolted down. It was stapled to a wire that went down the side of the house into the ground. A very simple thing that any local blacksmith could make. And yet what it did was something magnificent, which was that it intercepted a thunderbolt that would be about to strike a building and channel it harmlessly into the ground.
In 1752, he was able to convince other prominent Philadelphians to install lightning rods on important civic buildings. Lightning rods steadily proliferated across America and Europe.
The evidence is right there in black and white.
Alrighty. What are the key concepts that you learned from that video? Let's review that.
Everything has electrical charge.
Yeah, that's the first thing that they said, the significance, was that Benjamin Franklin discovered that everything in the world contained electricity. Okay. What else?
There were two different liquids of opposite charges, and he proposed it was only one that
Yeah, exactly. So,
They close one together and neutralize.
yeah, so they were doing these same exact experiments that we're doing here today. They're noticing that the leaf, once it touches it, then it repels it.
Mm-hmm.
They were doing these experiments like this one.
What they use, wood? Do they have plastic?
They use things like this. They call it Indian rubber, gutta percha is what they called it. It was more of a natural type material. But yeah, they had this type of, it was more of a natural, this thing has been charged already. So you can see that this, watch what happens here. Okay? Now it's repelled.
Right.
Why? They were doing these experiments and they were thinking about them and saying, what in the world is going on?
In two different directions.
Why was it at first it was attracted,
Because
and you touch it, and what happens?
when you touch it, it transferred some of the charge to the ball.
Yeah.
Right.
Did everyone see what happened just then? Describe what happened was Can you describe what happened?
Well,
Yeah.
it was attracted to it. Once it touched it, the rod transferred some of the charge to the ball, and then it repelled.
Yeah. Well, describing what happened, you would say it's first attracted to it, it touches it, then it's repelled. That's a description of just what happens. Then there's theories. Then there's theories on, okay, how do you explain what happened?
Right.
Okay, so the first part is just explaining that it actually happens. And what they were doing is they had discovered that this sort of phenomenon happened, and everyone's like, well, what in the world's going on? We don't know. That's weird. I mean, that's mysterious. So they started, maybe there's a fluid that exists that we can't see. It's so small that we can't see it, and somehow it's transferring to that. And so there are two theories. Is that there's some sort of invisible fluid in there that when it transfers to it, it has, when you rub it, maybe there's an opposite of that fluid. And when it touches it, then, but Benjamin said, I don't think it's that way. He said, I think that everything has only one type of fluid inside of it. And when you rub it, then you can have less or more of it. And if you have less or more, then more of the same kind, like if you have the same kind of that fluid, it seems to be repelled. But if you have the opposite of that kind, then it seems to be attractive. That's based on just experimentation. That's just gleaning information from experimentation, which is exactly what we can glean from here. And that is, when I touch it, first off, my body's conductive of, it's a lot of yucky liquids inside me. So I'm basically this liquid ball, right? Here's another kind of neat experiment. What if I touch it from over here? Oh, wait. Gotta get this thing stop moving. Hard thing is not to get it to. Ooh. Did you guys see what happened?
Mm-hmm.
What happened? What did I do and what happened?
You discharged the ball.
It did.
It was attracted
Electricity.
to the rod, but when you touched it from the other side, it immediately repelled from the rod.
Mm-hmm. Why? Why do you think it happened?
What electricity was in it was grounded. Does that have anything to do with you being grounded?
Mm-hmm. You want to do that again? I didn't actually touch it with the rod this time. I did something different. I charged it up. I got it close to it. I'm going to touch it. I'm going to touch the ball with my hand. You see what happened? As soon as I touched it.
Right.
Okay.
It went to the stick.
I shouldn't have let it touch. It's always kind of hard to do this.
Yeah.
Doesn't it seem to be a whole lot more attractive now than it was before?
It's magnetic. It's stronger.
By
It made it
touching
stronger.
by touching it, were you ensuring that it had a full opposite?
If you switch
Full
ends of the
discharge.
stick, will it do differently?
What's that?
If you switch the ends of the stick, will it do differently?
No.
Does it have anything to do with
No, I meant
polarity?
before you re-rubbed everything.
Oh, if I well, you can try it.
Does it have anything to do with polarity, Mr. Austin?
It's the same thing. Yeah. Okay, well, it's something to think about, right? Something to think about.
Yeah, for sure.
What else can I do?
See how wrong we can be on like those scientists, right?
Okay, I'll tell you guys what happened if you really want to know.
Yeah.
I was going to tell you on the slides, but okay, what happens? Okay. So first off, they found that by experimentation, if you rub plastic, hard plastic, it tends to gain electrons, which means a negative charge, and glass will tend to take on to lose electrons when you rub it, so a positive charge. But in this case, it doesn't really matter. But if you want to know the mystery, is that this has a negative charge all over it. When I put it up to this, the fluid inside of that ball, since it's aluminum, and so since that's a conductor, the fluid or the electricity inside of it can move around. So when I put it up here, all the fluid, all the electrons tend to repel the opposite side of it. Okay, that leaves the positive atoms bound with a positive charge. Okay, they thought of it like the positive charge comes over here, the negative charge comes over there, but it's one fluid. It's only electrons. When you speak of positive and negative, you're really defining it as two fluids, which you can think of it as two fluids, but it's not really two fluids. It's just but you can think of it either way, and it doesn't really matter. You're still going to get the same effect. So what happens is the first experiment is the electrons are getting repulsed by this negative charge, and so they're separating out inside that ball. Because they're separating out, it's attracted to the positive charge on the left side, because the positive charge on the left side is now closer than the electrons on the other side. So the positive charge on this side, see when I put my hand there, it affects it, doesn't it? I'm affecting the magnetic field. Okay? So the electrons are on this side of it, over here, and they're also attracted to my hand because they're charged. See, this ball is also... Okay. Now, what happens when I touch it with this? It actually transfers the charge to the ball. Okay? And then the excess electrons are now on the ball. So now it does not have a neutral charge. When I remove this, it's not neutral anymore. It actually has excess electrons. Most materials, if I touch it now, it's been neutralized. It has an equal amount of electrons and positive bound charge. The positive bound charge can't move. Only the electrons move. Okay? But when I touch it, it actually gains an excess amount, so that's why it's repulsed. Now, why does it get repulsed when I touch the other side of it? Okay, well, let's do that again. What happens when I touch the other side is that right here, what I'm doing is I'm separating out the electricity. Okay? The positive charge, I can't, it's hard to do this because it's around. Okay? So the electrons are on the other side, on the opposite side of the ball. Okay? And when I touch it, I transfer them to ground.
Right.
That's what's happening. But I can't. It's hard to do it and talk at the same time.
Is that why it's trying to spin?
Okay.
Trying to spin around to the other side.
So when I touch this side, I'm going to take all the electrons, the excess electrons, off this side of it. Now it's positively charged. The whole thing. All of its excess. So now it does not have an equal balance of positive bound charges and electrons. It's going to eventually get those electrons back through the air. They're just going to come in and hit it, and eventually it'll neutralize. And if I touch it, it'll neutralize. But right now, you can see it's really sensitive.
Right.
So, okay, so that's what's happening.
So if you rub...
So what other principles... Yeah, go ahead.
I was going to ask you, if I heard you right, if you rub the plastic rod with the wool sock, you gain electrons.
Yeah.
If you rub glass, you lose.
Yeah. So let's put some negative charge on there. So it's repelled to this negative, right?
Yes, sir.
So we've got negative on there, right?
Yes, sir.
Now, usually the glass doesn't work because it's really hard to get glass to work because it has water all over it.
Oh, really?
And it's really humid today, so it's probably not going to work.
Oh, okay.
But see, it's attracted to this.
Right.
So that tells you there's two different kinds.
Yes, sir.
This is a different material.
Yeah, it's mechanical friction. So the atoms with this sock and the atoms with this are reacting. Actually, what I'm doing here is I'm removing electrons from this, whereas over here I'm adding electrons.
Oh.
So is the sock charging
Yeah.
them?
Now I can do the opposite. I can touch this with that. Now it's repulsed to that, even though I knew it had an opposite charge, right?
But it will attract to that.
It's the opposite effect.
Now what's it going to do to this one?
It's going to attract.
Attract
It's
it.
going to strongly attract. So that's a proof right there.
Question.
Does it
Yeah.
react to the sock?
Well, I'm grounding it, but it will. It does have it, but see probably what it's getting off of it. But yes,
Right.
it does. what happens is these are both neutral, and you're exactly right. So you're a scientist. When you rub this, you're actually transferring from one electrons from this one to the other, so this one's positively charged. This one's negative now. But I'm touching it, and I'm wet, and all this stuff, so it's probably leaking off here.
Right.
You can also, it's kind of neat to see this hair and things like that move. Good?
Would the experiment work any differently if you had if you weren't grounded? Or would it be any stronger? Would the experiment be stronger?
The only reason it works is because this is an insulator and this is an insulator.
Right.
If I had a piece of metal here and I rubbed it, it's doing the same thing, but it's instantly draining off.
Right.
But if I stood on a piece of glass, then it would work.
Okay. All right, gotcha.
You can actually rub yourself, put yourself on glass, and they used to do weird stuff.
Right.
They did all kinds of weird experiments back in the day. Is everybody good with that? Convinced?
One question still.
Yeah.
So it has a lot to do with the object that you're rubbing and the object you're rubbing with. Which one has the most capacity for the electrons?
Yeah. Yeah, it does. Let's do that for a minute. Here's a different piece of material. This is what they gave me in the science experiment, but I actually like my little thing better. This doesn't work that good. This is what they gave me with the experiment kit I purchased. It doesn't work very good at all. This is a stake from my kid's little circle game in the yard where you throw it in and throw little rings around it.
Right. What material is the other one made of? Just the same
hard plastic.
Black.
Hard plastic. Now this.
Graphite.
That one's solid though.
This has a rough texture to it. It doesn't work very well.
Is that one solid and that one hollow?
This is hollow.
And that's solid.
Yeah. But I'm doing it on the edge. So, everyone good with that? Convinced? Okay.
I've got one more question. I think
Yeah.
kind of bugging me.
Okay.
Not since I saw this clip, but even before. The lightning rods. They
Yeah.
have the metal lightning rod. They have a metal wire going down the side of the building into the ground.
Uh-huh.
What keeps the lightning from going from the metal wire into the building anyway?
It travels the path of least resistance.
Probably, at least it's probably going to go through the least resistive path.
Right.
But that's a good point because we didn't really finish talking about the concepts that we learned from the video. What else did we learn from the video before the lightning rod? Because the lightning rod was the end of the discussion. So what else did we learn? We learned that there are two types of electricity.
Right.
We learned about atmospheric electricity. Actually, if you read the material the other day, then you learned that when things change from a liquid to a solid, when they solidify, there's an electrical effect that occurs there, sparks. And when things come from a liquid to a gas, there's an electrical discharge that occurs. So how does that relate to the atmosphere and the weather when something turns from a liquid to a gas?
Thunderstorm has a lot of updrafts causing a lot of...
evaporation.
Where does the rain come from? It comes from... It evaporates from the seas, the oceans, the Lake Norman. It evaporates from the sun. It goes up. It forms clouds. That separation causes electrical separation from there, and then that is up there separated, so it wants to be together.
Right.
And when it gets humid and when the temperature drops, the air can no longer hold the water because when the air is cooler, it can't hold any water.
Right.
So the rain comes because of the temperature, not drop in the temperature, not the opposite way around. Actually, the rain comes because the temperature drops, not the other way around.
Right.
So when that happens, the air is water in it. So water, it's going to encourage it to go ahead and spark across the air because now there's water everywhere.
Right.
So it makes it easier for the water to get down back to where it originally came from on the ground. So.
Would that be a similar example of what we call heat lightning? Just the lightning in the clouds?
Yeah, there's lightning in the clouds too, yeah. Yeah, if you ever see, then you'll see sometimes lightning in the clouds. It'll go...
Right. Would that be part of the process of going from a gaseous form to a solid?
Yeah, because when it's up there, it constantly condenses, turns back to water, and then turns back to gas back and forth. And the wind is blowing, and there's a lot of dynamics going on. Yeah. Okay, so really quickly other types of electricity, and then we'll do the lecture. This is a paperclip soldered to a copper wire. Okay, it's been found that if you join two pieces of metal like this, put a voltmeter across it, and then heat it up or cool it down, that it'll produce a voltage. Okay, and here's a perfect example: is a thermocouple. I don't know if you guys ever heard of a thermocouple. Mm-hmm. It is a okay. What it is, it's just two different types of wire with this little piece of metal. It looks like just a little solder blob right there. It's actually a little weld. Just two wires with a different type of material right there. That's all it is. It actually measures temperature. We use it in electronics to measure temperature. There's actually one over there on that $2,000 piece of equipment that we have. You would take this and you would use Kapton tape, and you would tape it to whatever you want to measure the temperature of, and then you would bring it outside into some sort of a voltmeter. And if I plug this, that's all this is. There's no magic inside of here. That's all it is. Two wires with a different type of metal soldered welded to the end. And if you can see the voltmeter here, hopefully something will happen. You see something? This is just cold air. What does it say on there? -3? Minus 0.003. Now if I heat it up, what does it say?
Going positive 5, 7.
Positive.
6,
okay.
5.
So that's because the rest of this is room temperature.
Right.
Now you're changing, you're causing a temperature differential. Lots of things. Almost everything that you do can cause electricity. I like the summary in the book. It said, almost everything causes electricity. So that's the world that we live in. Almost any type of change that you do, percussion, pressing things together. It said pressing a cork up against a piece of crystal. Just the pressure alone causes electricity.
So, is it, Mr. Elstead?
Yeah.
So, changing the physical state of any matter, is it causing electricity, or is it causing electricity to
separation?
Okay.
Voltage is a separation of electricity, really.
Is it emitting electricity, or it's already there?
Electricity. Okay, so what is electricity? Electricity is just fluid. It's just invisible fluid. Really, it's electrons. But before they knew that, they said it's just this fluid. It's kind of like water.
Right.
It's everywhere, right?
Yes.
Water is everywhere.
Right.
And electricity, us being able to measure electricity, is just a non-uniformly distributed electricity. If electricity was uniformly distributed everywhere the same, kind of like the air in this room, if someone goes over there and puts off a can of smoke, right, it's eventually going to fill up the room, but it's not uniformly distributed at that time.
Right.
But once it gets uniformly distributed in the entire room, you're not going to be able to tell a difference from here or from there. It's all going to be smoky in here.
Yes.
It's the same with electricity. You know, if you can't, it's when it gets separated and when you measure across. So voltage is an across variable, where current, when we talk about current and current electricity flowing, that's a through variable, goes through. And the analogy would be a water pipe. If you had a pneumatic tool in the middle and you had water coming, or air to power that tool, if there's no restriction of flow, then there's going to be equal pressure on both sides of that. If you put a tool in the middle of it and it's going to load that tool down, you're going to have different pressures on each side of it. That represents voltage. So you're measuring across. So voltage is an across variable, whereas if you measure the actual air flowing through that pneumatic tool or the water flowing through a pipe, that's a through variable, we call it. You're measuring something passing through. The analogy would be also maybe your car going down the road. How many cars go down the road at any given time? That's a through variable. Where across would be how many cars you have over here compared to over here. Okay. Well, the density of cars. Another type of source of voltage, what I usually do is I do all the demonstrations before the lecture and then I do the lecture. So another thing we're going to talk about today is other sources of electricity. This is a buzzer, and inside of this buzzer we have a crystal, piezoelectric, we call it. And if I put this battery, basically it's putting that It's putting that voltage across that crystal, and that crystal is vibrating. Okay. The opposite effect occurs as well. In fact, if I speak into this, it's probably generating voltage right now. It's vibrating that crystal, okay, and producing a voltage. So that's another source of electricity. We use crystal resonators in electronics a lot, and what that is it's really the same effect. The clock that controls a microprocessor is really a voltage across the crystal. And just like this thing was vibrating right there, that's exactly the same way the crystal in a computer or clock keeps your clock running. It's that heartbeat. You got to have that heartbeat to keep it going. That's the heartbeat that keeps every single computer, your iPhone, and everything working. Is that right there? If that was not working, it would be dead.
Can you repeat that, what you just said one more time, Mr. Austin? The last part of what you just said.
The crystal. There's a crystal inside of your computer and
inside
your phone and inside of this, and when you put a voltage across it, it vibrates.
Right.
Mechanically vibrates. Now, the smaller that is, the smaller that crystal is, the faster it's going to vibrate. The larger it is, the slower it's going to vibrate. So,
okay.
Yeah.
I thought it had to be two crystals separated by metal or something where they vibrate.
Piezoelectric effect is if you take a crystal and you bend it, you can measure voltage across it. There's different designs of crystals.
Oh,
There's different designs, but that's the fundamental effect. Yeah. We're not talking about magnets today, though. But we'll talk about magnets tomorrow, next class period. Yeah. We'll get into magnetism later. Yeah, so the only thing we haven't really talked about or demoed today is electromagnetism. And that's going to be your lesson that you're going to read.
Okay.
All right, so let's go ahead and work on the lecture.
Was the other electroscope not working?
What is 1140? Oh, yeah, I didn't show you the electroscope, did I? What happened to that little blue thing? Did I get the blue rod to anyone?
No, sir.
Oh, here it is right there. You know, I had problems with this electroscope. I don't know if it's going to work. Oh, yeah, there it is. You see that?
Yes, sir. How it opened up.
Yeah. How the electroscope... Oh. That didn't work out very good. Yeah, when I... Basically what this electroscope is a piece of metal. You've got an insulator, you've got the glass insulator, so it's all insulated so the electricity can't get off of it. That's the key. 2 aluminum strips, and when I put this up there, you can see that the leaves diverge, okay? But the interesting thing is if I take this and touch it, if I can get enough of the electricity on there, then they kind of stay diverged a little bit. I don't know if you can tell.
Yeah.
But it's so humid today that it's really hard to do experiments today on a very humid day.
It's kind of dark.
Yeah. So that is an electroscope. And you can actually use this to transfer electrons there, and then you can take a positive rod, and then you can see that whether it's positive or negative or not.
Right.
And you can also, this is an electrophorese. What you do here is you rub the plate. It should have negative on it now. And then we put the plate down here. Notice that it comes up pretty easy, right? Now if I touch it, actually I don't think it really worked very well. Just make sure it's nice and dry in here. Sometimes you have to rub it over and over again. First you have to get rid of the layer of water that's on it.
Yes.
If you can do it on a day like today. And usually that means get it hot. Let all the water evaporate. Mm-hmm. And then put this on there. I'll touch it. See how it's kind of stuck to that thing now, right? See the leaves diverged right there when I just did that? Now they're open a little bit.
Right.
Okay, so what that did was there's negative here. I put this on here. Actually, the charge on here can't move around. It can't flow out. And actually what really happens when I do this, it's actually only touching this thing on like 2 or 3 places. The rest of there's a very, very small layer of air. So it's not really transferring charge that much. What it's actually doing, we call it static induction. And what does induce mean? Induce means to force something to happen. If you induce labor, then you force labor to happen. So induction means you're forcing the electricity inside of it to separate. So what happens is all the electrons go on the top side. It's trying to get away from the electrons on the plate. So they try to get as far away. So they all wind up being on the outer surface of the plate. When I touch, and this is conductive, when I touch it, they all flow off. So it's left with positive all over this thing here. This is called electric force. And then I can transfer that. And you can do that over and over and over again. Actually, what they say, if today was not so humid as it is, then we could do that over and over again. And see there, it diverges even more.
Yes.
And you can keep doing this forever. Just keep putting it down, touch it, put it back. It'll continuously generate electricity over and over and over again. And that's the principle behind, I'll show you this really quick, just for dramatic effect. That's the principle behind this little guy here. This is a Wilmshurst machine, they call it. I'm going to get this thing back a little bit. Now, what this is basically that pie plate example, but they've got them on the outside edges, and then this is plastic. They got them on both sides, and it's doing that repeatedly. That experiment that I just did. Now, if someone would come over and touch one of these, it'd be really cool. Anyone want to touch it? No, I'm just joking. Don't touch it. Maybe he can do it, but it'll shock you. It'll shock you.
Now, have you measured the voltage
Here,
coming off of it?
Let's see how much we can get. It's very high.
54 stars.
If you come over here really quick, I'll show you how this works. Now, we want to get back to your lightning rod question. Someone had a lightning rod question, right? How does this thing work? Okay, see these little plates here? This is like the electric force that I just showed you. What happens is a charge naturally just builds up those naturally, and when they get close to another one, what do? They cause charge separation on the other side, right? Charge separates out on this side, and then it runs across this little thing that discharges it, right? So now it's left with a positive charge. Now what happens when it comes over here to this point? What was the whole idea with the lightning rod was what has been discovered with points. When you put electricity on a surface, if it's round, then it evenly distributes everywhere. But if it has a shape other than round, then there's more on the corners. There's more on sharp edges and points. The electricity builds up on sharp points. In fact, if it's sharp enough point, it completely leaks off through the point. It'll leak off through the point and go into the air. Okay? Sharp points. Now, so Benjamin Franklin discovered this too, and so he said, well, what if I put a sharp point sticking up into this space? Maybe his idea was not that lightning would strike it, actually, which is the video was wrong. His idea was that it would dissipate the electricity out of the air and lightning would never strike it. That was his idea. That it would suck the electricity out of the air so that it would never strike that building. Now, who's to say? Maybe they do. Who knows? But that was his idea, and it seemed to work. But it does. If lightning does strike, it will go through the rod. So, but the whole idea was to get rid of that. So that's the principle. Sharp points. Electric induction. Induction means charge something, charge a device, and when you, let's say that this is charged, I transfer some charge here. Induction would be if this is positively charged, if I move this up to here, the electric fluid inside of this will separate out. If this is positive, the negative side will come over here, the positive side over here. If I touch over here, the positive will go away, the negative is going to be bound. It can't move, it can't get away. When I move it back, the negative is going to be there. Or if this is negative charge, same thing happens. The electrons will be repelled on this side, the positive will be over here. If I touch over here, the negative side Even if I touch here, these ones that are bound will not come off. It doesn't matter what side you touch it on. Those ones that are bound to this, they won't move because that force is so strong. You can touch it anywhere you want. It's going to separate out. It's going to go to the ground. And then when you release it, it's going to be charged. So that's induction. And that's the basic principles of how capacitors work. We'll talk about capacitors later. It's also the basic principle of how ESD, electrostatic discharge, can damage a component. It's the number one failure mechanism in electronics industry. And it's something that will destroy your phone or your computer or whatever.
What is that now?
Electrostatic discharge, ESD.
Okay.
We'll talk about that a little bit more in the lab today. Okay? Now I'll just go over the quick lecture. Okie doke. Okay. So we demonstrated these today. Two types of electricity. Conductors. We'll talk a little bit about conductors, key concepts. Okay, so we talked about electrical attraction. I think you guys know what that is. It was discovered by the Greeks in 600 BC, and they first found the property with amber. Okay, this is a thing of amber. If you want to pass around something. This has a kind of an aid there. Piece of amber, and so the Greek word for amber is electron. So that's where we get the word electronics. Is actually it means amber. So when you say electronics, you're saying amber-ix, really. But amber also is the same thing we use. It's tree sap that's hardened, but tree sap is also what we use. It's kind of funny, but we use it in soldering to prevent oxidation. So we use tree sap. We also use in the printers, in the copying machines, we use toner, which is amber that has been ground up really fine because it has electrical properties of attraction. And that's how you actually dye the amber black. Okay, and you put it. That's why toner is so expensive. It's expensive because it has that amber in there. It's a natural element. It's an insulator, so it can be electrified. Okay, when it's electrified, then I'll show you a quick video on that. Electrical attraction. Okay, we did this experiment where we showed that attraction exists. It works with anything, actually. Iron, gold, brass, everything. It actually works, but you have to insulate yourself when you do those. And originally they didn't do that. And then electrical repulsion is, again, the experiment that they did to show that there's two types of electricity is the fact that sometimes there's attraction, sometimes there's repulsion. So that's where we get the whole idea of positive and negative. And we did that experiment. Okay. And we talked about Benjamin Franklin's experiment. They talked about positive and negative. It's not really positive and negative, it's just an idea. The two are opposite. Now, how does electricity differ from any other fluid? We talked about electricity being a fluid. What are some similarities? What are some differences between electricity as a fluid and water as a fluid, for example? Yeah.
Water can be formed into a solid state, gaseous state.
That's true. So he said water could be formed to a solid, liquid, or gas. That's true. Electricity, we don't know that property exists. What else? It's not visible. That's true. Well, actually, it is visible. Plasma. It's what when people say plasma, that's what they're talking about. The aurora, things like that. You're seeing the electrical effect and magnetic effects come together. But plasma, electricity, you're seeing the effects of it. But yeah, I guess you're right. You don't. Water's. Yeah, you kind of see the effects of water too because you're seeing it as it bends light. So, yeah, you're seeing the effects that it has on light because water's kind of clear, and water has impurities in it. So a lot of times you're seeing the impurities of the water and the effect that it has on light. What else?
Water's affected by gravity and pressure.
Okay, water's affected by gravity and pressure. Electrons actually, they originally thought that electricity had no mass, but as it turns out, electrons do have mass. It's really, really small. It's probably the smallest thing that we know of that has mass. But you actually can weigh. Like there's a guy that spent 20 years or something up in his apartment trying to capture electrons, and he'd measure the weight by doing something. I can't remember. But yeah, he became famous for measuring the weight of an electron. What else?
Flow. Like flow. It's similar to water and.
It flows. So that's a similarity.
Flow different.
Okay, so the similarity is that they flow. So they both can flow. That's true. What else? One difference is water does not repel itself. Okay, electricity does. Electricity has a property where it repels itself. Yeah, at the molecular level, it's really close. Yeah. Electrons theoretically would attract themselves because anything that has mass is attracted to, but the electric force of electron is going to overpower the gravitational force of it. So it's all orders of it all is about relative strengths of things. So yes, water. From a gravity standpoint, every object that has mass is attracted to every object that has mass. But since the Earth is bigger, everything's attracted down. As it turns out, so those are some good examples. Yeah.
Gravity affects water, and it doesn't affect electricity, or does it?
It does actually, but you can't. It's affected so small because electrons' mass is so little.
Right.
It doesn't affect it that much.
Right.
But you can't actually measure that. Okay, that's good. Those are some good things that are similarities and differences of electricity and for example, water. Here's an important point. Neither kind of electrification is produced alone. Electricity cannot actually be created, nor can it be destroyed, which is the same principle as the conservation of energy. There's lots of different conservation laws. There's a law that says energy can neither be created nor destroyed. That's the law of conservation of energy. All the energy we have in the universe is the same. It only gets transferred from one place to another. Same is true with electricity. We cannot create electricity. That will help your understanding of electricity to realize that you can't actually create it. You can only transfer it from one part to another. You can separate it. Eventually it all comes back together. What goes up must come down. It's the same with electricity. What gets separated eventually comes back together. Maybe not those same electrons. Maybe those electrons go over there and new electrons come in. And it constantly has new electrons coming in and out. So there's always an equal quantity of both kinds produced. One kind appearing on the thing rubbed, just like you discovered. That one kind appearing on the thing rubbed, that is, his comment was that are these both charged? Yes. This has a positive charge, this has a negative charge. And then when you bring them back together, then you could neutralize them back out. The minus electricity of the rubbing cloth, okay, we already talked about that. Okay, this is kind of a neat thing. I'll show this really quick. How does a laser printer work? This is a good application.
Welcomely reproduced here, but an assembly of more than 80 different components, performance engineered exclusively for the printer for which it was designed. It's the heart of the printing process. How does a laser printer transform characters into hard copy? There are 6 distinct processes involved in producing a laser-printed page, all of which occur within the cartridge. Lexmark laser technology uses an electrophotographic process to transfer digital data to paper. The process begins with the charge roller, which applies a uniform charge to the surface of the photoconductor drum. Photoconductor drums are highly sophisticated components, precisely formulated to the power and wavelength of the laser print engine for which they are designed. The laser strikes the photoconductor drum up to 65 million times a second, creating a chemical reaction that discharges the areas that are negatively charged, resulting in an electrostatic image. Next, the image is developed. The toner adder roll coats the developer roll with toner while electrostatically charging the particles. As the toner is placed on the developer roll, a leveling device called a doctor blade evens the toner to a thickness of approximately 15 microns, just slightly thicker than a strand of silk. As the developer roll and photoconductor drum come into contact, the negatively charged toner is attracted to the discharged areas of the drum. When the paper passes under the drum, the transfer roller applies a slight electrical charge, causing the toner to move from the drum to the paper. The drum rotates up to 2 revolutions per second, timed with the exact speed.
Everyone catch that? She's kind of going fast. What they're doing is they're basically charging, let's just say for example, they're charging the paper. The paper is an insulator for the most part. They're charging the paper positive. It'd be easy to do that, right? Okay, you can just rub it, or you can just emit electrons on it with an electron beam or something, which is the basic principle of how TV works, is electron beam. So positive charge, if you charge the toner negative, what's going to happen? But what happens is actually they charge this entire drum up opposite of the paper, and then they use an electric beam to neutralize the places that they don't want there to be ink. So when it goes past the toner has, if this has positive, this has negative, then that would have positive and they attract, and then, so they're always doing this back and forth, positive and negative. Do you want it to attract or do you want it not to attract? So that's what's going on. Pretty cool application. Whoever invented this had to know this stuff really good.
Of the paper, ensuring a complete image transfer. Next, the image is made permanent through a combination of precisely controlled heat and pressure. As the paper approaches, the fuser rollers heat up to 225 degrees Celsius. In just 23 thousandths of a second, the powdered toner reaches its melting point and bonds onto the page. The melting point of Lexmark toners are specifically formulated for our printer's fuser temperatures, ensuring satisfactory prints and protecting the life of the fuser. The final step in the imaging process readies the cartridge to print a new page. The cleaning blade gently removes any stray particles of toner, and the drum is ready to be written anew. During the life of an average Lexmark cartridge, this electrophotographic process is repeated more than 100,000 times. With so much at work, it's clear to see why we recommend our customers use only original Lexmark.
Okay, we'll buy it. We'll take it, right? Looks good.
We'll buy it.
We don't need any more sales pitches. So that's a good practical application of everything we talked about today, right?
Right.
We're going from 600 BC to today, right? With electricity. That goes to show that if you're really going to be, if you really want to not put any limitations on yourself, I'm not going to put it past someone in this class may invent something someday. But if you really want to be at that level to be able to do that, you have to know a whole lot. You need to be very well-rounded. Very well-rounded. I would read old books.
It only took them 8,000 years ago.
Yeah. Some people are, theorists. Some of them were like Edison, Thomas Edison. He put everything to practice. That's what I liked about him.
Right.
This is the triboelectric series. This is a little bit more elaborate than the one in the book. This is from YouTube. Basically, what it says is they came up with this series by doing all these experiments and just, trial and error, basically. No one's a genius here. Just trial and error. And like Edison said, it's inspiration. Its success is 1% inspiration, 99% perspiration. It's just a lot of hard work, trial and error type thing. Polyurethane foam, hair, nylon, glass. If it's if it's on the top, let's say you rub these two things here. Whichever one is above is going to acquire the positive charge. Whichever one's on the bottom is going to get the negative charge. So they put these in order by just doing all these experiments. So you can see rabbit's fur. So the best thing probably would be if you rub polyurethane foam with ebonite, it would produce the most charge, probably. But anyway, so that's called the triboelectric series. Just know that it exists, know how to use it. If I say, if you rub this with that, what is the glass going to be? Well, it's going to be positive. But if I rub this with that, the glass is going to be negative. Right? Pretty easy to use, right? So you don't have to do all those experiments. We already talked about fluid charge. The quantity of okay, let's talk a little bit about this. Franklin said that the one with the excess fluid was positive, but after we came up with molecular theory and things like that, somebody said that electrons are negative charged. Someone else probably decided that, and then when they brought the two theories together, they didn't mesh up. So he wasn't necessarily right or wrong. It's just when they did molecular theory, they said that it had negative charge. So what that means is now when we say current flows, we use, even today, we use what's called the conventional current flow theory. Conventional means we're using Franklin's idea that positive charges are the ones that are mobile, which we know electrons are mobile. So most textbooks have, well, some textbooks have both the conventional current flow and electron flow. You have to, now we're using conventional flow. Some people today are using electron flow. If you use electron flow, all the symbols are backwards, and everything comes up through the ground, which I think is weird. And the diode symbols don't make any sense, and nothing makes any sense. And really, it's all arbitrary anyway. Because who says that electrons have a negative charge? It's just random. You could say that they had a positive charge. So it doesn't really matter. So we're going to just use the conventional flow just to make everything easier. If you don't understand what that means, then you'll understand later when we go on further. Charge. When we talk about charge, we say that charge is the quantity of the electrification of either kind of spoken of charge. So if I say that this has more charge than this, then that's the quantity that we're talking about. And we kind of like a dozen of eggs, right? We talk about a dozen of eggs. You don't talk about one egg. You group them up. So when we talk about charge, we group a bunch of electrons together. Millions of electrons. We call that 1 coulomb of charge. So 1 coulomb of charge is millions of electrons. Well, I'll tell you what the number is. It doesn't really matter what the number is. Just the fact that we have a really big number to say, okay, we're not going to count every single electron. We're just going to group them together. And we call that a coulomb, and we call that charge. So if a 1 farad capacitor has a charge of 1 coulomb, it's going to have 1 volt. That's the way we define it. It's clear that there are charges of different value as well, of different kinds. So the charge can have also not only, we can say 1 coulomb, 2 coulombs, 3 coulombs. We can say it has a positive or minus to denote whether it has an excess electrons or excess electrons or deficiency of electrons. If you want to be technical. When the charge of electricity is moved, we use the term discharged. Hey, when I touch this, it's called discharged. This is just terminology. Good conductors of electricity are instantaneously discharged when we touch. We already talked about that. Poor conductors may be discharged by touching the entire surface. Now, it is interesting to note that if I charge this plate, if I touch it here, this plate's not going to be discharged. Just the place I touched will be discharged. Okay? Otherwise, the toner printer cartridge thing wouldn't work. Okay? If I go like this, okay, probably I got all the charge off of it. That's because that charge can't move on the plate because it's an insulator. Now, this thing, when I induce the charge now, it can move all over this thing. I mean, it's all actually uniformly distributed. Actually, where's most of the charge going to be distributed when I do that? If there's charge on here, where's most of the charge going to be? On the edges, because we say that they migrate to the sharp points.
Right.
And a lot of it's probably going to go off of it.
Yes, sir.
To have a good one, you'd have to have a nice round edge on it.
Yes, sir.
Poor conductors can be discharged by touching the entire surface with the hand or passing through a flame. Flames have electrical properties too. So when you see a flame, electricity everywhere. Okay? Electricity may reside upon the surface of bodies, static charge, or may flow through the substance. I'm talking about current. Current is a through variable. Okay? Whereas voltage we talk about as a difference in amount of charge. A lot of people trying to get a hold of me today. Every time you hear that beep, that's an email or something. But actually what I could do, since I don't need that anymore, I can just mute that. What else? Some substances... Okay, the term conductor. What is a conductor? It's applied to those bodies that allow electricity to easily flow, like metals, human body. Many substances are partial conductors, like wood, silicon. They just kind of conduct. Glass, silk, plastic, resin, oils are non-conductors. Isn't it kind of weird that oil is not a conductor? That's why you have oil inside transformers. The oil cools the transformer, but does not conduct. You couldn't put water inside of a transformer; it would short it out if it's high voltage. It would cause a lot of leakage inside. But here's the thing: nothing conducts. Even metal doesn't conduct perfectly.
Right.
And no insulator is a perfect insulator.
There's no.
That's where we get the idea of resistance.
Mm-hmm.
Okay? The idea of resistance is you can't really call something a conductor or an insulator. You can just say that it has a certain resistance. If something has a very, very high resistance, it's called an insulator. If something has a very low resistance, we call it a conductor. If something has a moderate resistance, we call it a resistor. That's really what we do. So the idea of resistance takes into account that the world that we live in is not perfect. And Michael Faraday coined this term dielectric, which is inside of a capacitor. We'll talk about that a little bit, but that means through or across an electric dia means through. And then, of course, we have electric. Gilbert gave the name of non-electrics to those surfaces. Okay, we don't really need to look at that too much. Electrical experiments fail in damp weather. It's explained by the knowledge that water is a conductor. Just imagine doing this a long time ago and people were like really confused. What the heck is going on? Sometimes it works, sometimes it doesn't. But we have this moisture everywhere. Electrical effects. I didn't show you this, but you can take a straw and you can put it on a needle and you can make it spin. It's kind of cool. So the straw needle electroscope. We have the golden leaf electroscope that I showed you. This was what was used to prove all this stuff and come up with all these theories. There was this instrument here. You can make your own electroscope, which is what I did. Put a cork, and then this represents a high charge, medium charge, and a no charge. So this is no charge, medium charge. Inverse law of squares. I wish this thing would go away. There we go. Inverse law of squares, Coulomb's law, says that the force between two small electrified bodies varies inversely as the square of the distance between them. What does that mean? Well, that means that if I have this rod is electrified, then that means the closer I get it, the more force it's going to be on it. You can tell. It's like over here, it's not. Over here, it doesn't really move around that much. But what this is saying is, if I half the distance, the force is going to what? Double. If I half it again, it's going to double again. Okay. Conversely, if it's attracted, I move it back, then it's going to 1/4, 1/4, 1/4, or 1/2. I'm sorry, 1/2, 1/2, 1/2, right. And keep 1/2. So it's inverse squared relationship, which is the same as what? That equation is the same as what?
Gravity.
Same equation. Yeah. As you double the distance from the... If you have a certain... Say you put a spaceship up in the sky and it has a certain force. Now if you double the distance from the Earth, it's going to half. It's going to half, then do it again, it's going to half. Eventually up on the moon, when you get up high enough, you're not going to have, it's not going to be any effect at all, which is sort of like that little ball. Think of that like the Earth. You're over here. Out here, things don't affect it. But when you start to get really close to it, you start to feel the effect. Same with the Earth, with the gravity. As you get far away from the Earth, you can't feel it.
Why does he say small bodies? I mean, 2 electrified bodies wouldn't make it.
What's that portion between? Well, a large body is going to be affected a lot by gravity. So what he means by small, the same reason that we balance this stuff on, if we balance this stuff, you're canceling out gravity. Small things have, gravity's not affecting it. You have to cancel out the effect of gravity. One way to cancel out the effect of gravity is just have it so small that gravity's not a factor.
Right.
Is gravity a big factor for this feather that I had here?
It's on the second shelf in the back.
Oh.
It fell.
See, gravity's not a huge impact on this. I mean, you can see it falls a little bit. But the whole idea is light bodies cancel. You don't have that effect of gravity.
Right.
Okay. So you have to separate out what you're trying to test and what you're not wanting to test. So this is Coulomb's law, which looks almost exactly like Newton's universal law of gravitation. In Newton's law of gravitation, instead of Q1 and Q2, you have M1, M2, which is the mass. And then you have the gravitational constant, which he came up with, and then you have R as the distance squared, so it's the same thing. And Einstein was working on his unified theory of everything. He thought that he could unify everything, but he never could. Because he surmised that there must be some reason why that's true. Why gravity and electric fields, they all have the same equation. But he was not able to do it. But and the induction, what is induction? There's different types of induction. There's electromagnetic induction. We talk about magnets, but this is a different type of induction. Induction means to force to happen. If you induce labor, you force it to happen. Induction means we're going to force the electricity, we're going to cause the electricity to be separated. So induction means if I charge this ball with positive, what's going to happen if I get it close to this object? What's going to happen is the electricity inside this object is going to separate out. It was neutral. The negative is going to come over here. The positive is going to come over here. If I touch this with my finger, okay, then this is what we call bound. These electrons are going to be bound to this ball. They're not going to be able to move. Even if I touch it over here, right here, if I touch it right there, they're still not going to move. If you touch this, then the positive is going to come out of it. And the negative is going to be what we call bound. It's not going to move. The middle region of this shows no sign of electrification in this case. 2 electrons opposite at the ends, the side farthest being positive and negative. Okay. This is conduction. This shows that a piece of wood set on a tumbler to prevent it from shorting to ground will cause the electricity to separate, and then on the other side you'll have paper. It's going to be, so that proves that wood is conductive. It appears that a positive charge attracts a negative and repels positive. This influence can be a considerable distance. You can take a wire or something and string it if you use silk strings or something. It's not going to, and you can communicate a long distance, and that's what they did in some of the first experiments. Is they would do this experiment and they would put it on a wire and it would communicate all the way to the other end of the building. I thought it was pretty cool because they never had anything like that before. So charges disappear and leave no trace behind. When the electrified body is removed, both the charges disappear and leave no trace. Okay, so there's no adverse effects when you separate electricity and bring it back together. If the conductor is made in 2 parts, and then you cause induction to occur, and then you separate those, they're going to be. So if you have 2 eggs like this touching, and you cause induction, you can actually separate the eggs out, and you can see that they have a positive and negative. So it separates out the electricity. Let's see here. If the conductor be placed in contact with ground, then that end only which is nearest to the electrified body will be found to be electrified. The repelled electricity is indeed repelled as far as possible into the earth. We already talked about that too, or we demonstrated that. One kind of electrification only is under these circumstances to be found. Okay? In induction explained, we talked about that a little bit Now, why did the ball, so when I touched the ball over here like that, when I electrified it and then touched it, why did it jump around so much? It seemed like it was just had this erratic behavior. Well, what happens actually is when I have a charged rod here of plus, and then I have a minus, if I have a, oh, I'm sorry. I thought this was I thought this was PDF or PowerPoint. If I have a plus here, what happens is, now that we know Coulomb's law, we know that the minus is going to be attracted to the plus, and it has to do with the distance, right? Coulomb's law says it has something to do with the distance. So the only reason this is attractive is because these separated, but the minus is closer to this than the plus. What actually is happening here is this minus charge is attracted to this. The plus side is actually repelled from this. So the plus side is actually pushing it away. It's actually pushing this away.
Right.
And this is pulling it towards. But which one's going to win? The one that's closer.
Right.
That's the only reason you have attraction. So what happens when I touch this side of it? This one's bound, and the positive stuff comes off. Okay? Another way to say that is electrons actually go on it, but it doesn't really matter how you think of it. Just think of it as the positive coming off. Now, there's no positive on here to repel, right? So now all of a sudden it's going, wow, it's going to fly towards it. And if you make sure that you hold this so that it actually can't touch it, or maybe just gets close to it, then it'll just fling up and start doing all kinds of stuff. So that's induction explained. Knowing Coulomb's law is critical there. You can show that if you have a copper wire here and you put it next to this wire, you can cause an effective electroscope from a distance. I guess you could call this the first telegraph. And if you have a nylon cord, no conduction. So that's the concept of a conductor and insulator. Conductors would include silver, gold, iron, copper, etc. What's the best conductor? Gold, silver, or copper? No, silver is the better conductor. What material has the least contact resistance? When two things are pressed together, like sockets and things like that, that's contact resistance. What has the least amount of contact resistance? Gold. That's why things are gold plated, not because gold has the least conductance. If you look it up on a chart, silver is a better conductor. Silver is more expensive, so we use copper.
It oxidizes. Silver oxidizes.
Right.
Yeah. So gold, the reason we use gold to plate these pins and stuff is because it has the least amount of contact resistance. Insulators include glass, plastic, rubber, wood. Okay. Well, I think conduction, most bodies can be classified as either conductors or non-conductors. However, large classes of substances occupy the intermediate place of partial conductors. Dry wood is a bad conductor and also a bad insulator. That's why we call it a semiconductor. But wood is a good enough conductor for very high voltage electricity, but it's a bad conductor for low voltage electricity. And that's more easily explained when you get into the theory of resistance. That's why we need the whole theory of resistance. Because really resistance tells you the full story. You can never really classify things as really conductors or insulators. Substances that are very bad conductors are said to offer greater resistance to the flow. There is indeed no substance so good as to be devoid of resistance. There's no substance so high of resistance as not to conduct a little. Even silver, which conducts best of all known substances, resists the flow of electricity to a small extent. And we did one series. We did the triboelectric series. Tribo, I think, means rubbing. Tribo means rub in Greek. Triboelectric. So you push the two terms together. Electric was rubbing electric, right? Silver, copper, other metals. So this is. Oh, notice that charcoal is on here. Is that surprising to you? Charcoal is a good conductor. What did Thomas Edison use to make his light bulb? Charcoal is basically what? Carbon.
Right.
What all is carbon? tons of stuff made out of. Yeah, diamonds are carbon. Did you know that carbon has many different structures, molecular structures? Depending on its structure, it can be either a diamond that's really expensive, or it can be charcoal, or it can be graphite, or it can be different things. You can actually take a pencil and draw on a piece of paper and measure the resistance, and you can make current flow through just drawing on your paper.
Right.
You can make current flow around your page with just drawing on it. That's carbon. Carbon was used to make the first light bulb. Basically, the thing in your fireplace after you burn a fire is carbon. The yucky stuff inside your engine is carbon. It's what's left over from the burning process. And so it was basically a string coated with carbon was the first light bulb. And bamboo. Water, the body, cotton, and then you got oils. Actually, oil is not a very good conductor. It's kind of... I'm surprised that it's right there.
Well, it says it's at the top of the non-conductor.
Oh, okay, that's true. It's a non-conductor. Okay. Distribution of electricity, it remains at that point and does not flow over the surface. Okay. That's important for your printer over here. If glass tube is rubbed in it, only that one end is electrified. So this is for insulators. Conversely, if a charge of electricity is imparted on a conducting body, it instantly distributes over the surface. Generally, though, not uniformly. Remember, the points have the highest. Now, if you have this electrified and you have a point here, you can actually, the electrons will flow off. They will actually blow a flame. Okay? Yeah, the electrons will come off of it. So, what they didn't know that we now know, mystery is solved, is that the source behind all this strange phenomenon is electrons and atoms. It's the smallest component of every element. You can see that the proton, the nucleus, is what we call positively charged, and the electrons flow around, so there is only one fluid, I guess you could say, unless you called this a fluid. I mean, if this... this we typically, in a solid material, we say is bound, because it's actually part of whatever it is you're playing around with. For example, copper or whatever. If this atom was in a piece of copper, then this part of the element would be in a specific spot. It'd be able to vibrate around with heat and stuff. It vibrates around. These things are all touching each other. There's a metallic bonding or covalent bonding, different types of bonding that these things bond together. But once they bond together, they don't really switch positions. They vibrate and things like that. But the electrons, in the outer shell of the electrons, they do transfer between electrons because they all have the same electrons, so they can share those electrons. Okay? Now, how easily they can share them depends on whether it's a conductor or an insulator. So that's the mystery to that. Electrons, we say he has a negative charge, but that's arbitrarily decided. Protons, we say has a positive charge. Neutrons, we have no electrical charge. If this has atomic number of 4, that means that there's 4 protons, there's 4 neutrons, and there's 4 electrons. Okay, if it loses an electron, we say that this is a positive ion. If it gains an electron, we call it a negative ion. We say that it has been ionized. Okay, now that is going to be attracted or repulsed by something. Which is here, you see negative, extra electron, negative, missing electron, positive. We also say electrons, free electrons can move at high speeds through metals, gases, vacuums. We can say that electrons are at rest, or we can say that they're in motion. This is what we're going to talk about on Friday, current electricity. This is what we call static electricity. ESD is important here. When you charge up a body and you touch it, they rush off like this, but it's instantaneous almost. It's current, but it's instantaneous current. If you have a battery, you can actually create a continuous flow of electrons, and that is what we call current. And that's what I'm talking about on Friday. Surface causes to be negative charge. I think that's about it. This is a little bit more. There's this book called Getting Started in Electronics that these slides come out of. Really good book from Radio Shack. This is the one that I learned electricity when I was a kid, and that's how I'm in electronics, so if you want to go buy it. It's still there today. And other sources of electrification, percussion, heat, almost anything can cause electricity to occur. And that's about it. Go ahead and read the book if you want to learn more about that. And we did those experiments. So go ahead and do the reading assignment. you want to prepare for lab today, you can. I can give you some of the instrument manuals if you want to look through them, flip through them. But they're in the back there on that wall. There's a power supply manual and a digital multimeter manual, and I'll bring those out and put them on the desk so you guys can kind of flip through them if you want to before class and get prepared a little bit. Good? Any questions? It's getting started in electricity and electronics, and the cover looks different today, but they do still have them, but they look more modern. And this guy, Forrest M. Mims.
Oh yeah, we wrote that down yesterday.
The third. I think I put that in the syllabus.
Right.
But it's a really good book for learning the basics of electronics. It has little projects in the back you can do, and you can buy little kits from Radio Shack and all that good stuff. Any other questions? All right.
I couldn't get that Eagle Cat on my computer, so I guess I'm going to have to do it here to school.
Okay. You can work on it here, that's fine.
I kept saying something about my software would help me.
I will try to post those slides on Moodle so you guys can go through them again if you want.
Lecture slides?
Yeah, the lecture slides. Those would be good things to study for the test. That in 3 weeks we have a test. So it would be good to study those. Make sure you read the book. Things like that.
So we go from metal shelves on golf clubs to graphite shelves on golf clubs. Both of them highly electric.
Really? Yeah? Probably so.
But a lot of them get zapped down in
Oh, really?
Florida.
That's funny. Like, why do we keep getting zapped?
Do they have an icon for that? For that Eagle Cat stuff? What does it look like?
Yeah.
What's some of the icon?
It looks like an eagle. This is a red eagle on it.
It's not there. I guess it's on the non-light. I guess I'll have to bring it up on the cart.
That's where you're doing that.
Yeah, 6.2. She's the latest version. Yeah.
That's what we're doing, that fabrication design.
Yeah.
I guess I'm having to
I can do it on my computer at the house. It won't load.
I'm going to go eat something.
I'll go there.
And if
You guys can hang around if you want, and I'm going to go eat. And I'll be back.
Thompson, will you, after lab, will you have a few minutes to maybe help me? Well, if I can get my computer downloaded, I'd like to get it downloaded on my laptop.
Oh, okay. You have Wi-Fi? Call the Wi-Fi help desk and make sure you get Wi-Fi connection.
Okay. All right. Thanks.
Good.
Mm-hmm.
And, there may be other people in the class that have computers and they can help you.
Did
You guys have a computer with you today? Yeah, yours. Okay, he did it yesterday and got his working. So if you have,
work, brother. Yes. Okay.
so they may be able to help you, like if you have questions about it.
Go through the libraries or projects?
All you gotta do is call that number and I'll send it to the guest account.
I already had all that done, brother. It's still, I don't know why it's not letting us back on. But I'll get on it here and there. I've got this
Just create a new project. I'm gonna have to go.
Okay.
You can access and help for someone else. I'm gonna have to head on out. I'll be back. I'll be back in about an hour, and I can help you a little bit later.
Thanks. And for lab that day, you didn't have no kind of homework or anything you said, because I missed that lab. one day.
Yeah, I didn't have any.
Okay, good deal. Good deal. And all we've got for a homework day is read some more reading to do.